Next we look at distance to stars. We have already seen that the angle on the celestial sphere, the angular distance is a measure of how far stars are in the sky. But now we move away from this concept of all the stars being stuck on the celestial sphere and try to understand how can we estimate the distance to the star, because in reality stars are in 3D space. So, is there a way to measure the distance of the star from us? So, the common distance units are usually light years or astronomical units, and which are familiar. Light year, as I mentioned earlier, is the distance travelled by light in 1 year, which is given here, and astronomical unit is the average distance between the sun and the earth. I say average because there is a slight ellipticity to the earth's orbit around the sun. There is another distance unit which is commonly used, which is known as a parsec. The linear distance is 1 AU, the angular distance between these two objects is 1 arc second, and therefore, the distance to these two objects would then be 1 parsec. Now, distance is a very important parameter because it helps us estimate the total brightness of stars as well as many other important parameters. So, one always tries to find out distance by various means, and there are many methods to find out the distance to stars. The closer stars, one can find out distance using a method called parallax, but there are other methods as well, which is known as moving cluster method. There are variable stars which are used as distance indicators. At different distances scales are used, or different methods of estimating distance are used. In this presentation or talk, I will only talk about the parallax method, which is for the which is used to measure distance to relatively close by star. So, this parallax method is a very simple trigonometric method to measure the distance to a close by star with respect to very distant stars, and this is because of the apparent motion of the close by star with respect to distant stars due to the effect of Earth's revolution around the sun. As can be seen from this figure, the nearby star would appear to be at different locations for an observer when he observes 6 months apart. And if he is observing continuously, he will observe that the one star seems to make a small circle in the sky with respect to the other distant stars, and this small circle would have a radius of p as is shown in the figure. So, p corresponds to this parallax. Remember, p represents half angle of that this star subtends over 6 months. So, therefore, let us look at two cases, one is January and July. In January, for example, the star would appear to be towards, because we see only the effect of projection, we would see that the star is between the two stars on the right, but then as time goes by and if one makes an observation 6 months later, one would see that this star has now moved towards another location in the sky, and if one observes this star continuously, one would see that this star subtends a circle in the sky. And this effect is known as parallax, and using a simple trigonometric relation one can estimate the distance. So, tan p is given by 1 AU by d, because 1 AU is astronomical units, which is the radius of this radius of the circle of that the earth circular path that the earth takes around the sun, which is taken to be approximately circle, and d is the distance to the nearby star. When one uses the small angle approximation, then tan p is almost equal to p, and therefore, the distance of the star can be taken as 1 AU by p, where p should be in radians. If p is in arc seconds, then one has to convert it to radians appropriately. If one converts p to arc seconds, then one finds that d corresponds to what is known as the distance unit of parsec. This is how we had defined the distance unit, that distance unit of parsec, that is the distance to two stars which subtend an angle of roughly 1 arc second and are separated by 1 AU. Using this method of parallax, the distance to the star can be estimated. So, if d is the distance and p is the parallax which is measured in arc second, then the distance in parsec is given as reciprocal of the parallax in arc second. So, that is why it is known as parsec. Okay. Now, what are the typical parallax values? So, the nearest star, Proxima Centauri, has been found to have a parallax of around 768 0.5 milliarc seconds. So, as one can understand this the parallax depends on the distance to stars, and for nearby stars one can measure the parallax because the angles are larger. For as the stars are more distant, it is more difficult to measure the parallax because the angles become smaller, and therefore, the distances are also start becoming uncertain. And this for example, Proxima Centauri corresponds has a parallax of 768 milliarc second, which corresponds to 1.3 parsec, which is 4.2 light years. There have been a number of space missions to measure parallax and therefore find the distance to a large number of stars, because as mentioned earlier, distance is a very important parameter in estimating the other properties of the star. Hipparcos was one such mission by the European Space Agency in which functioned between 1989 and 1993. It is a high precision parallax collecting satellite. Of course, it is named also in honor of the ancient astronomer Hipparchus. It measured the positions and parallaxes of nearly 118,000 stars. The more recent mission which is still functioning is the Gaia mission. It was launched again by European Space Agency ESA in 2013. It is still operating. It has an accuracy of around 25 microarc seconds, and recently released data a catalog has the positions and parallaxes of around 1.3 billion stars. So, these catalogs can be used to identify a given star, its accurate position and its parallax, and the parallax can be used to determine its distance. And this parallax motion is an apparent motion. It is distinct from something known as the proper motion of the star, because proper motion of the star relates to the actual motion of the star in space, whereas parallax is what is apparent because of the revolution of the earth around the sun. And again, so if the star, for example, as shown in the figure, a star is moving in space with a certain velocity, which can be denoted by a 3D vector, then it can be this 3D vector can be translated into one vector along the line of sight and another vector, tangential vector, in the plane of the sky. So, the vector along the line of sight is known as the radial velocity, and the tangential vector in the plane of the sky is known as the proper motion, and this proper motion is seen as the motion of the star in the sky. And how would one distinguish between parallax and proper motion? Parallax is for example, something that recurs, that is after year you would see the same path of the star because it is an apparent motion. Because of the revolution of earth around the sun. On the other hand, proper motion would mean that the star continues to move in the same direction always, and this is related to the peculiar velocities of the star. Sometimes stars have a certain velocities, and this proper motion is measured with respect to the sun or the solar system. And this again, these proper motions are much larger and can be measured more easily for close by stars as compared to stars which are more distant. And if distance is known using this proper motion, the actual linear velocities of the star in space can be derived. We next move on to understanding brightness of stars can be measured. What are the units that are generally used? Before we start with understanding the various units, I would like to define certain terms. So, the first is flux density. So, flux density from the star corresponds to the energy received from the star at earth per unit time, per unit area, per unit frequency interval. That is, if one has a detector of a certain area dA and what measures the radiation coming from the star in time dt, and if the detector is actually measuring within a frequency interval d nu, then the flux density, also known as specific flux, is given as dE, which is the energy being received by per unit area dA, per unit time dt, per unit frequency d nu. One can similarly also define the flux density in terms of lambda, where one uses a wavelength interval instead of a frequency interval. However, f nu and f lambda are related by the relation lambda f lambda is equal to nu f nu, and therefore, f nu is given by lambda square by c f lambda. Another unit is the luminosity, and luminosity corresponds to the total energy radiated by the star per second. So, this corresponds to power, therefore, its units are either watt or erg per second, and the more common unit with respect to stars is the solar luminosity. It is also known as the bolometric luminosity, but very often one also measures the one also gives or quotes luminosity over a specific frequency range or a specific wavelength range. In that case, it is known as a specific luminosity. For example, if one were to measure the energy being received from the sun per unit area, per unit time, then one can measure this very easily, and this turns out to be 1344 watts per meter square, and this is also commonly known as solar constant. Now, how is the luminosity related to the flux density? As one can see, the flux density corresponds to the energy per unit area per unit time, whereas the luminosity corresponds to the total energy per unit time. Therefore, the flux density is given by luminosity per unit area. So, one can consider, as shown in the figure, top right figure, if one considers a spherical wave front, then if you consider a small area dA over which it is energy is being measured, and if the distance at which it is being measured is given by d, then the flux density is given by specific luminosity by 4 pi d square, where d is the distance to the star from earth. We also very often define another unit for measuring the light coming from stars and galaxies, more often for galaxies rather than stars, that is known as specific intensities, because this is generally described for extended objects and cannot be defined for point like objects like stars, and this is the energy being received per unit solid angle, per unit area, per unit time, per unit frequency, because for an extended objects one can measure how much is the energy being received per unit solid angle from the source, and if that object is makes an angle of theta with respect to the detector, then one the specific intensity is defined as I nu cos theta equal to the energy being received dE by dt, the time interval over which it is being measured, the frequency interval per unit area and per unit solid angle. So, these are the terminology which is commonly used to quote the radiation from stars. A more common measure of brightness in the optical, and of course, now also in the IR and UV, is something known as magnitudes. So, this is a very historic concept, and it relates the brightness of the stars on a logarithmic scale, and the apparent magnitude measures the light of the star as we see it from earth. So, in earlier times the brightness of the stars were classified into various classes, and the brightest stars were categorized as magnitude 1 and the faintest stars were categorized as magnitude 6, and because this is the range over which our human eye is sensitive. This corresponds to a magnitude difference of 5, and since the response of the eye is almost logarithmic, this magnitude difference of 5 corresponds to an intensity ratio of 100. That means one magnitude difference corresponds to a ratio of around 2.5. Using this as a standard, a more rigorous definition of magnitude is given by the following equation. If there are two stars with magnitude m1 and m2, then m1 minus m2 is equal to minus 2.5 logarithm of f1 by f2, where the f1 and f2 represent the fluxes of the stars 1 and 2. The negative sign indicates the inverse scale, since the brightest stars are magnitude 1 and the faintest stars as detected by the eye are magnitude 6. The magnitude 6, for example, represent the limit of the eye's sensitivity. If one uses telescopes or other optical aids, then one can measure even the magnitudes of even fainter stars. The earlier definition of a magnitude was a relative definition, where if you know the fluxes of two stars, then one can get a magnitude difference between the two stars. But a more rigorous definition would allow us to define a star with certain magnitude equal to 0. So, Vega is generally used as the standard, and its magnitude is considered to be 0 across all the optical wave bands. So, if one measures the flux from Vega whose magnitude is 0, then this actually gives a rigorous definition to the magnitude, apparent magnitude, which is given by m equal to minus 2.5 log 10 f by f naught, because the magnitude of vega is 0. The figure below shows the apparent magnitudes of the commonly objects visible to us. Sun is very bright, as we know, and its magnitude based on the flux that we receive, flux density that we receive from the sun, its magnitude corresponds to around minus 26. Sirius, the brightest star, its magnitude is minus 1.4, and full moon is when it is very bright corresponds to a magnitude of apparent magnitude of approximately minus 12. Now, apparent magnitude corresponds to the magnitude as measured from Earth for stars located at different distances. So, if a star is close by, then it will appear brighter to us, and if the same star were at farther distance from us, it will appear fainter to us. Therefore, to have a more uniform comparison, another magnitude scale is defined, which is known as the absolute magnitude. This defines the magnitude of a star when it is located at a constant distance of 10 parsecs from us. So, therefore, the absolute magnitude is the apparent magnitude of the star if its distance is 10 parsec from us. This is therefore distance independent and gives a measure of the luminosity of the star. Therefore, if you know the absolute magnitude of a number of stars, the one that is brighter is also more luminous. And this leads us to the relations m1 minus m2. Here of course, absolute magnitude is denoted by capital M is equal to minus 2.5 log 10 of L1 by L2, where L1 and L2 corresponds to the luminosity of the stars. And if sun were one of the stars, then since we know the luminosity of the sun, and if we know the luminosity of any other star, then we can calculate its absolute magnitude using the relation given below. That is, absolute magnitude m is equal to the absolute magnitude of the sun minus 2.5 logarithm of the luminosity of the star in solar luminosity. So, this in this slide one can see the effect of the apparent as well as absolute magnitude. If you see the left hand side figure shown below, the circle on the left shows the Canis Major constellation as visible to us. The size of the circle or the star represents the corresponds to the brightness as we see it, the apparent brightness. We see therefore, Sirius is very large and there are other stars in the Canis Major constellation. And these stars, as mentioned earlier, this is a constellation, the stars are at different distances from us. If all these stars which are visible in the left side circle were brought at the same distance of 10 parsec to us, then the luminosity or the brightness is what would be the absolute brightness, absolute magnitude, and this absolute magnitude is shown in the circle on the right hand side. And one can see therefore, that Sirius no longer is the most luminous, but rather the other stars in the constellation are more luminous than Sirius. On the right hand side, a table is shown showing the limit, sensitivity limit, that is how faint different optical aids or devices can go. For example, with a binocular we can see stars up till plus 9 magnitudes. With the naked eye, as I already mentioned, it is plus 6 magnitude, and for a 200-inch telescope one can actually go up till plus 20 magnitudes, that is very faint. Now, if one knows the absolute magnitude and apparent magnitude of a star, then it is possible to calculate the distance of the star. This is because the apparent magnitude is the light that measured as we are receiving on Earth from a star located at distance d, and absolute magnitude corresponds to the light being received at Earth for the star when it at a distance of 10 parsec. Using these two relations, one can derive a relation between the apparent and absolute magnitude, and this relation will therefore have the distance term d coming into picture, and this can be easily derived, and it is shown in the following relation, where the apparent magnitude minus absolute magnitude is given by 5 times logarithm of d in parsec minus 5. And in the table below one can see the distances corresponding to different distance moduli. For example, the distance modulus of 0 would mean the apparent and the absolute magnitude are the same, and therefore the distance is 10 parsec, and distance modulus of 1 would correspond to around 15.8 parsec, and distance modulus of 20 would correspond to around 100 kiloparsec. Now, we have defined the apparent and absolute magnitudes, but astronomers, when we measure it, we measure them using detectors, and if we want to compare the magnitudes, we would like to have certain standards, that is wavelength ranges over which we can measure and compare. So, what is usually done is the light that is received from the telescope is passed through certain filters, with filters whose characteristics are very well defined, so that the light being received through one filter, if the same filter is used by two different observers, then the magnitudes can be easily compared. So, there are certain standard filters which are used by observers, and for example, the optical filters which are known as Johnson-Cousins filters are shown in the figure below. What is shown is the transmission curves, that is the wavelength, different filters are shown, the U, B, V, R and I. These for example, let us take one of the filters, U filter for example. The pink curve shows the U filter. As the radiation is coming through, then what percent of that radiation is transmitted through the filter is denoted by this curve. The radiation that passes through the filter is then converted to magnitude and used to compare with magnitudes measured by others. If an alternate set of filters are used, then the equations are derived relating one set of filters to the other set of filters for comparison, else it is not an appropriate comparison. These Johnson-Cousins filters are one of the most standard set of filters, and the most common ones are the ultraviolet U, the blue B, the visual V 551 nanometers, the red which is at 658 nanometers, and I infrared which is at 806 nanometers. So, when one defines magnitudes, when one measures magnitudes through these filters and quotes the magnitudes as measured through certain filters. These are the filters through which the telescope Gaia is measuring the magnitudes of the star. And here for example, the transmission curves of the Gaia filters are shown. There are two sets of curves, one is the curved lines and one is the gray lines. The gray lines represent the measurements that were made prior to the actual experiment, because this is a space measurements, and the onboard space measurements of the transmission of the filters were found to be different than what was measured on Earth, and they are shown by the colored lines. The colored lines transmissions are those which are used to measure the magnitudes of the stars as measured by Gaia. So, this table for example lists the various parameters of the Johnson-Cousins UBV RI filters, and there are also infrared filters here shown, the JHK. The name used for the filter is shown in the first column. The second column shows the central wavelength, approximate central wavelength of the filter, which is used because a filter is characterized by a central wavelength and a certain width, the bandwidth of the filter. And the third column gives the bandwidth of the filter, and the fourth column gives the zero magnitude flux, that is the flux of Vega through these filters, and these are then used to estimate the magnitude of a star through the given filter. And from the apparent magnitudes, one can then, if one distance is known, one can estimate the absolute magnitudes. The apparent magnitudes are also, although they are represented by the small alphabet mu, mv, they are very often also represented just by the alphabets u, b, v and r. And I would like to mention here that the flux density of Vega is given in a certain unit known as Jansky here, and this Jansky unit is mentioned below. It corresponds to 10 power minus 26 watts per meter square per hertz. Apart from this, there is also another magnitude system which is commonly used very often in ultraviolet and in some other filter systems, even in some optical filter systems such as SDSS. This is known as absolute magnitude system or AB magnitude system. This does not represent the absolute magnitude capital M that I mentioned earlier. This is still apparent magnitude, but it is called AB magnitude. In this, Vega is not the standard, but a certain value of flux density is used as a standard, and this value of flux density is the constant across all the filter bands. Therefore, the flux measurement is calibrated absolutely, and it is given by MAB minus 2.5 log 10 f nu by this 3631 Jansky. Whatever be the frequency over which the flux density is being measured, the AB magnitude is calculated using this. This allows us to get rid of using a star like Vega at across filters where it may not be radiating very efficiently. And very often these kind of AB magnitude systems are used in ultraviolet. Next we move on to radiation from stars. How we understand the radiation from stars. The spectrum of a star is well approximated by a black body curve. This can be shown from this figure. Here the red shows the actual spectrum of the sun. When I say spectrum, it is the light received per unit frequency interval. So the intensity or the flux density measured as a function of wavelength is known as the spectrum. This is well approximated by a black body curve shown in blue, whose temperature is 5780 Kelvin, which is the surface temperature of the star. So, if as the spectrum is well represented by a black body curve, the properties of the black body can be used to understand or derive properties of the star. Therefore, the effective temperature of a star can be obtained by fitting a black body to the stellar spectrum, and the surface temperature can be obtained by using the Wien's displacement law, that is the lambda max into T effective is a constant. One can also use the Stephen-Boltzmann law to get the radius or the luminosity. Since the star has a finite surface which is given by 4 pi r square, the total energy radiated per unit time is the luminosity, and therefore luminosity is equal to 4 pi r square sigma T effective power 4, where sigma is the Stephen-Boltzmann constant. Using this relation, one can see that depending on the temperature, the peak wavelength of the black body or the stellar spectrum shifts, and as most of the radiation will be close to the peak radiation, it helps us get an idea of what the star would look like. A hotter star would therefore appear blue as compared to a cooler star which would appear red. This also helps us define a more technical quantity known as color index, and this color index corresponds to measurements of flux densities across two filter wavelengths. In this figure, one shows various black body curves, and as one can see, the peak of the black body curve shifts in accordance to the Wien's law. If B1 and B2 are two filters, then if one measures the flux through these two filters, the ratio of the fluxes would give an estimate of the difference in magnitude. Therefore, if one measures the magnitude of the same star in two different filters and one use the difference between them, then that corresponds to the color of the star as it corresponds to the ratio of fluxes. So, for black body, this ratio of fluxes would be unique corresponding to a given temperature. Therefore, this color index, which is the difference in magnitudes in two filters, which also corresponds to the ratio of the fluxes, can be used to estimate the surface temperature of the star. We have defined the magnitudes through filters. Then there is one can also define a magnitude corresponding to emission across all the wave bands. That magnitude would is known as the bolometric magnitude. So, it is a measure of the total energy. One can get an absolute bolometric magnitude as well as an apparent bolometric magnitude if one considers emission at all the wavelength range. The convention is usually to measure this magnitude in the V filter and use a certain correction factor known as the bolometric correction to get the bolometric magnitude. So, that is given by this relation: bolometric correction is equal to apparent bolometric magnitude minus the apparent magnitude in the V band, and this bolometric correction is usually modeled very often using black body curves, because if one knows for a particular black body amount of radiation received in the V band, then one can calculate what would be the effect of the measurement of flux across all the other wave bands. The bolometric correction would be unique for every different black body, and it is found to be very large for very hot and very cold stars. This is because the measurement is in V band and most of the emission is away from the visible. This can also be used to estimate the luminosity, and according to the IAU convention, this luminosity can be related to the bolometric, absolute bolometric magnitude by the following relation, 3.0128 into 10 power 28 watts into 10 power minus absolute bolometric magnitude by 2.5, and the absolute bolometric luminosity for the sun is found to be 4.74. Here are a list of books and other resource material, few textbook suggestions are given, and there are links to few animations. Please go and try out some of these animations, as they will help you understand the sky better. Thank you.